So section 7.2 focuses on integrals involving expressions with trigonometry. So we know, for example, the antiderivatives for sine and cosine, and that's okay. We could find the antiderivative of sine times cosine by using the double angle formula for sine, and then just doing a u substitution on that. But what do we do if we have higher powers? For example, if I had cosine of x quantity cubed in an integral, what would I do to try to solve that? Well, what we learned last time was integration by parts, but I don't actually want to go down that route because I'd really just kind of end up going in circles and I wouldn't get anything useful out of it. But the answer for pretty much all the integrals in this section is actually going to be u substitution. And we're going to have specific rules based on what we have in our function. So here I have 3 cosines, and I need to try to do a u substitution. But the derivative of cosine is a negative sign, and I have no sines available in my function. So I'm going to make some. So what we do is we use identities to force the problem to fit a form. And we're really just going to use basic ones. We're going to have sine squared plus cosine squared is equal to 1. So I'm going to take 2 of these cosines in here, and I'm going to turn them into 1 minus sine squared. So this is cosine of x times 1 minus sine of x quantity squared. And what that's allowed me to do is say, hey, I can let u be equal to sine of x in a u substitution, because then my du would be equal to cosine of x dx, which is exactly what I have written here. So what does that give me? That's going to give me the integral of 1 minus u squared du, leaving me with u minus u cubed over 3 plus c, which is equal to sine of x minus sine of x cubed over 3. Now, I'm not going to do a large number of these because we literally just have a laundry list of, if you have this, then do this. So general form, I'm going to have cosine to the n of x times sine to the m of x. So what do I have here? If n is odd, then I'm going to change semicolon, no, comma. I'm going to change all but one cosine into sines. I'm going to do that using the Pythagorean identity I wrote above. So I'll say cosine squared of x is equal to 1 minus sine squared of x. Then use u equal to sine of x in a u substitution. And I'll do that exactly like I did the first example. Similarly, if m is odd, I'm going to change all but one sine into cosines. And here I'm going to have sine squared of x is equal to 1 minus cosine squared of x. And then we'll use u equal to cosine of x in a u substitution. Now, if they're both odd, then I can make whatever choice suits my fancy. So, if they're both odd, maybe go with the smaller number. But, you know, there are some other shortcuts I could go around with this. Like if they were both the same odd number, or if they were both the same number, I could rewrite this as a single power of sine of 2x, or something along those lines. For this section, you really want to be on top of your trig identities. But many of these will have multiple solutions. Now, I do have an uncovered case here. What if neither of them is odd? What if they're both even? So if both m and n are even, then what I'll have to do is one of the so-called power reduction formulas. Now, I say power reduction, but what I really mean is one of the half-angle formulas that you can find at the front of the book for sine and cosine. So if they're both even, we'll use half-angle formulas. To kind of cut everything in half, so to speak. So that is sine squared of x equal to 1 minus cosine of 2x all over 2, and cosine squared of x is equal to 1 plus cosine of 2x over 2. Now, I don't have to change anything before I use these half-angle formulas, but it will simplify your multiplication if the number of sines and cosines is either balanced, or if all of them are sines, or if all of them are cosines. But what may happen is you'll end up turning one integral into several integrals. So, after I use the half-angle formulas, we'll just re-evaluate what we'll need to do. So let's do one where they're both even. We'll find that it actually turns into literally every other problem. Let's have the integral of cosine squared of x times sine to the fourth of x dx. So, if we try one way, where we just substitute everything immediately, we're going to end up with the integral cosine squared is equal to 1 plus cosine of 2x. So this is 1 plus cosine of 2x over 2. And sine squared is 1 minus, so this will be 1 minus cosine of 2x over 2 squared. And if I multiply that out carefully, I'll have a 1 minus cosine of 2x multiplied by 1 minus cosine squared of 2x all over 4, which leaves me with, let's see, I'll have a 1 over 8 times 1 minus cosine of 2x minus cosine squared of 2x plus cosine cubed of 2x. And this kind of unfortunately always happens, but now I'm stuck with, well, every power of cosine I could come up with. But what I'm going to do is I'm going to group together the odd ones, and I'll deal with the even ones separately. So this is 1/8 times the integral of 1 minus cosine squared of 2x dx plus the integral of negative cosine of 2x plus cosine cubed of 2x dx. Now I can actually get away with something here. For the integral with the even ones, I could use the Pythagorean identity before using the half-angle formula to reduce it, or I could just jump straight down and use the half-angle formula. In general, if I have a lot of even terms, I'm going to want to use all the half-angle formulas first. And then for the odd ones, I'm going to do like I did for the first problem. I can keep the cosines around here because they kind of factor out, but I'm going to turn as many cosines as I can into sines and then do a u substitution on that. So for the first one, I'm going to have the integral of 1 minus, and since cosine squared of x is 1 plus cosine of 2x, but I have a 2x already here, I'm going to have 1 plus cosine of 2 times 2x, so 4x, all over 2 dx. Plus, I'll leave this guy alone for now, but I'll write it this way. So I have 2 over 2 minus 1 over 2 minus cosine of 4x over 2 dx plus, let's save this guy for later, which is 1/8 the integral of 1/2 minus cosine of 4x over 2. And I would do u substitution for that. So I'll say u equals 4. No. I have to split my integral first, because if I do a u substitution involving this cosine, I'm not going to have a du attached to this 1/2, so I won't be able to finish that integral. So I'll write this as integral of 1/2 dx minus the integral of cosine of 4x over 2 dx. Now I can use a u substitution on this one, and the du will be 4 dx. And this first integral, that's just going to be 1/2 x. So this is 1/8, open parentheses, 1/2 x minus, this turns into 1 over 8 times the integral of cosine of u du. But that is just sine of x, or sine of u, but u is 4x, so we'll just say this is sine of 4x. We'll throw the plus c on right here. So now we can work on the integral we've been saving up so far. So I have 1/8 1/2 x minus 1/8 sine of 4x plus the integral of cosine cubed of 2x minus cosine of 2x. So I'm going to change all of these cosines into sines. So I have cosine of 2x times 1 minus sine squared of 2x minus cosine of 2x dx. Leaving me with the integral, I could write as cosine of 2x times the quantity 1 minus sine squared of 2x minus 1. where the ones will cancel. Now I could use two u substitutions on this, or one really good one. If u is equal to sine of 2x, then my du will be 2 cosine of 2x dx. So my cosine of 2x dx is equal to 1/2 of du. Giving me the integral of u squared over 2 du. But that antiderivative is easy. It's just u cubed over 6 plus c. I think I had a plus c earlier, but it disappeared. Nope, I guess not. That's okay. I got it here. You can assume your plus c is already taken care of if you still have integrals left to do. Then I should switch back to x's. 1/2 x minus 1/8 sine of 4x plus sine of 2x quantity cubed over 6 plus c. So we got one of those to look forward to. But it doesn't matter how many you have, it just gets longer. Now, if we have stuff for sine and cosine, we also have stuff for secant, tangent, cosecant, and cotangent. The secant and tangents go together, just like sines and cosines go together, and cosecants and cotangents go together. So what I'm about to write for secant and tangent applies exactly for cosecant and cotangent. So if the number of secants, if n is even, we'll change all but 2 secants into tangents. And the reason for that is the derivative of tangent is secant squared. So the antiderivative of secant squared is going to be tangent. But since we're going to have both tangents and secants, I'm more interested in the u substitution, which causes tangent to have a derivative of secant. So that's going to be my du. So this is secant squared of x is equal to 1 plus tangent squared of x. But it's important that you always remember to save 2 of them for the du. Actually, I don't need to capitalize that. And then we're going to use u equal to tangent of x for u substitution. If m is odd and n is greater than or equal to 1, then save 1 tangent and 1 secant, and change all of the others into secants. And that's going to use tangent squared of x is equal to secant squared of x minus 1. And we're going to use u equal to secant of x for u sub, where the du is going to be secant times tangent. Now I had the requirement of n is at least 1 on this one because I needed to have 1 secant as part of a du. But in reality, as kind of a sub-bullet, if n is equal to 0, then I'm still going to change all but one tangent into secants. What's going to happen here is your integral is going to split for these, and some of them, some of the tangents are going to have secants attached so that you can use a u substitution, which is fine. But there's going to be at least one, or there is going to be one, where you're just going to be integrating tangent by itself. If n is equal to, not n, m is equal to 1, then we'll just use u sub. Tangent of x is equal to sine of x over cosine of x. So what's missing out of this? What happens if n is odd and m is even? Well, in that case, we're just going to change everything into secants. And then we're going to use integration by parts on that. And there's something, a recursive formula that exists for these problems. So I'm going to do secant cubed, and then I guess I'll make you guys do the rest. So, first, let me show you what happens for tangent cubed, and then I'll show you what happens for secant cubed. So tangent cubed of x, this is going to be equal to, what I said was you change all but one tangent into secants. This is going to be the integral of tangent of x times secant squared of x minus 1 dx, which is equal to tangent of x secant squared of x minus tangent of x. Now the reason I brought this up is however many tangents I have here, I'm going to have a whole bunch of these secant squared of x's minus 1s. And what's always going to happen after I multiply it out is I'll have a whole bunch of secants with one tangent attached to it, and then one tangent at the end standing alone. So I'll split this into two integrals. So for this first one, I would do u equal to secant of x, and the du is therefore secant of x times tangent of x dx. And it's important to have at least one secant to deal with that. So then I'll get the integral secant times tangent, so tangent in one of these secants is the du, and I'll have one secant left over. I'll have u du, where this u is the one secant, and the du, if I write it correctly, is going to be secant times tangent dx, minus what's over here, tangent of x dx. So this is u squared over 2 minus the integral of tangent of x dx. So let's undo this first u substitution. So I'll have secant of x quantity squared over 2 minus the integral of sine of x over cosine of x dx. which if I choose u equal to cosine of x, then my du is equal to negative sine of x dx, which leaves me with plus the integral of 1 over u du, giving me the final answer of the natural log of the absolute value cosine of x, in addition to my other stuff. So you always got to break off that one last extra tangent when you have that case. And then finally, if I had secant cubed, or in the corresponding co-cases, if I had cosecant cubed, I would also do this. Is I would actually split this into an integration by parts problem. And write it like this. I'll have secant of x times secant squared of x dx. So the secant squared of x, I can take the antiderivative of that just fine. But the secant of x, I can't take the antiderivative of quite so easily. So I'm going to let my u be regular secant of x, that one, and my dv is going to be secant squared of x dx. So those guys. Leaving me with a du equal to the derivative of secant is secant times tangent dx, and my v is equal to tangent of x. So I have, from integration by parts, uv, secant of x, tangent of x, minus the integral of v du, which is tangent of x times secant of x times tangent of x dx. Which looks great, right? Wonderful. But let's see, I have 2 tangents and 1 secant. What do my rules say to do about that? Two tangents and 1 secant. Well, that's exactly the same problem I started with. So I'm going to change everything to secants. So I have the integral of secant cubed of x dx is equal to secant of x tangent of x minus tangent squared is equal to secant squared minus 1. So this is the integral of secant of x times secant squared of x minus 1 dx. So I have the integral of secant cubed of x minus secant of x. And here I'm going to use the techniques we did for a couple of those special problems in integration by parts. Is I'm going to split this integral so that I have a copy of my original integral. So I'll have minus the integral of secant cubed of x dx minus minus, so plus the integral of secant of x dx. And what this happens to all of these problems, even if I started off with secant to the 11th, I would end up with a slightly smaller version of basically the same problem. So I'll take this, add it to that side, and now I'm just left with the integral of secant. So how do I handle the integral of secant? Well, technically that's a u substitution. So what I'm going to do with that is I'm going to multiply and divide by just the right thing to make everything work out. So this is the same as the integral of secant of x times secant of x plus tangent of x divided by secant of x plus tangent of x dx. So if u is equal to secant of x plus tangent of x, the denominator, then my du will be secant times tangent of x plus secant squared of x, or secant of x times secant of x dx. And if you notice, that's exactly what I have on the top half of this problem. So 2 times the integral of secant cubed of x dx is equal to secant of x tangent of x plus the integral of 1 over u du, which is secant of x tangent of x plus the natural log of the absolute value of u, or the natural log of the absolute value of secant of x plus tangent of x plus c. So as a final answer for this, secant cubed has an antiderivative of 1/2 of all of this. So I encourage you to come up with some general formulas for, I guess, power reduction for secant and cosecant, those integrals, because those could certainly pop up in the worst times. But basically, if you're faced with a product of a bunch of trigonometric functions, you should approach it, after turning everything into sines and cosines, you should approach it with these guidelines. Now, there is an additional technique which will actually solve any rational function that's given in terms of sine and cosines, but we won't be able to touch that until section 7.4, where we do partial fraction decomposition, because it actually turns into one of those problems after you do it.